let's discuss this very important concept in physics called the circulation of a field. And actually, it's very easy for me to define the circulation of a field to you, because the circulation of a field, let's write it capital gamma, this is a Greek letter, yeah, is equal to an integral f dot dr, but with a circle here, okay, on a curve C. And what does this circle mean? It simply means that the curve C along which we do this integration is a closed path. Okay, so actually many of our previous examples that I solved where we did the integral along a circle, that was a circulation. Okay, so whenever the path is closed, so what do I mean by a closed path? So your starting point is equal to your ending point. Okay, so this is a closed path, and therefore if you calculate the circulation along this path, so closed curve. So if you calculate the integral f dot dr along this path, this is called the circulation of the field. I'm not going to spend time explaining why this is important, because we will talk about that in the next chapter on vector calculus. But maybe just as a taste of what is to come, think about it. For example, the gravitational field always has a circulation that is 0. And why is that? Well, if you think carefully about it, if you could find some circular path in which the circulation of the gravitational field was not 0, this means that you could let a mass in free fall, so it would start following gravity, right? So we are saying that gravity is pushing the mass on the direction, and it would come back to the same point, but with a bigger kinetic energy, because it has been accelerated. There has been a net positive work done on the mass. So you would get energy from nowhere. So this means that whenever you have a gravitational field and other kind of fields called conservative fields, then the circulation of those fields is always 0, no matter which path you choose. As long as it is a closed curve, the integral will always be 0. Okay, so that's why this will appear a lot in physics. It also appears in physics if we look, for example, at Maxwell's equations, yeah, in SI units. So you can see Maxwell's equations contain lots of flux. You already know that, the flux of the electric field, the flux of the magnetic field. It has triple integrals of rho dV. This is like the total charge. And then it has this here, which is E dot dl. Notice that Wikipedia uses dl. Let me zoom in. So Wikipedia uses dl instead of dr. Okay, but this is a bold L, meaning that this L is a vector. Okay, so it's a dl vector. It's the same thing as dr vector. You can call it dl. So this is the circulation of the electric field, which is equated to some time derivative of the flux of the magnetic field. And also here in Ampere's law, you also have the circulation of the magnetic field equated to some kind of flux of the current density and a flux of the electric field with a time derivative. Okay, so you can see that clearly physical laws involve lots of multiple integration, both triple integrals, fluxes, and circulations. Okay, very good. So let's do an example of a circulation in the next video.